All right, let's take a look at the questions I assigned from section 1-2. So this section was all about solving equations where we can separate the variables. So let's look at this one. Looks like our independent variable is x, so I will rewrite y prime as dy dx. dy dx equals x squared over y times 2 plus x cubed. All right, so I would like to get all my x's on the right, all my y's on the left. Remember, let's write down, at least for this first one, what's the finish line? I would love to get my equation in this form. You know, f of y dy equals g of x dx. And remember, with integrals, integrals, no matter what we do with them, always harken back to this idea of areas of rectangles, which means I am multiplying vertical values. So evaluating a function, like what's the value, like what's the vertical value times a small change in x. So basically what's a height times a width, that gives you the area of a rectangle. So why do I bring that up? To further remind you that I need to be multiplying by dy and dx. So I point that out for two reasons. I need to have my variables agree. So for example, I can't have like, what's a good counterexample with this one? For example, I can't do dy over x squared. I definitely could divide x squared on both sides. That's absolutely legal. But in this case, it wouldn't help me integrate. Something else that's totally legal is I could do 1 over dx equals x squared over y over 2 y times 2 plus x cubed dy. Dividing by dx and dy doesn't really help us either. We need to be multiplying by dy dx. All right, so quick reminders. So now let's try to get to this separation of variables. So I think I can make that happen by multiplying both sides by dx. So dy equals x squared over y times 2 plus x cubed dx. So I believe the x's are fine. I've achieved getting all the x's with their dx on the right, but then I also have to divide through by y or multiply by y. So I get y dy equals x squared over 2 plus x cubed dx. So now I think the variables are fully separated, which means from there we are able to integrate. So when we integrate, what do we get? We get 1/2 y squared equals, what does this thing become? So rule of thumb I always like to follow when I have a fraction like this is compare two things. Look at the function in the denominator, 2 plus x cubed, and think about what its derivative is. What is the derivative of 2 plus x cubed? In this case, that's 3x squared. Do you have that derivative in your numerator? Kind of. You don't have exactly 3x squared, but what you do have is a multiple of it. So what I'm going to do is this. I'm going to cheat a little bit. I'm going to say, all right, well, I'm going to make 3x squared appear in the numerator, but I can't really do that without reinserting balance here. So I'm going to multiply the inside of my integral by 3 and multiply the outside of my integral by 1/3. Another way to kind of show you that this is going to shake out the same way is this. we can set up a u substitution. If u is equal to 2 plus x cubed, then du is equal to 3x squared dx. And let's clear the decks again. Let's go back to what we left off. So hopefully you can see that 2 plus x cubed is in the denominator. That's a u. And what else remains is x squared dx. I don't really have x squared dx, but I can solve for it. If I divide this equation by 3, I get du over 3 is equal to x squared dx. So basically what I have in here is du over 3u. So what do integrals look like if you have, and I'll pull out the 1/3. What do integrals that look like du over u become? They become natural logs. So this becomes 1/3 of the natural log of the absolute value of 2 plus x cubed. Need a constant of integration? I will put it on the right-hand side. You can put it, basically it has to exist somewhere. And also you can evaluate the constant of integration whenever you want. I'm gonna do it now. Never mind. There's no way to do that in this one. Okay, so we want a general solution. So what does that mean? That means I want to isolate y. So we have a couple steps to do to get there. From here, how do I isolate y? Well, I need to double both sides. So multiplying both sides by 2, I get y squared equals 2/3 natural log of the absolute value of 2 plus x cubed. I could say plus 2c, but an unknown constant, which is doubled, is still an unknown constant. So we kind of take some liberties. I'll still call it c. If you called it 2c, beautiful. That's fine. Now how do I isolate y? Now I got to square root both sides. So y equals the square root of 2/3 natural log of the absolute value of 2 plus x cubed plus c. All right, so, and I did not give you a data point. So I did not give you a corresponding XY pair. So that is as far as we can take the solution for this. All right, next, unlike this where we have an initial value, we have a data point here. So first we need to separate the variables. So I believe in this case, we can cross multiply. So that gives us y dy equals sine of x dx. So variables are separated. So let's integrate. So we have 1/2 y squared. Integral of sine of x should be negative cosine of x plus c. And one of my personal preference things, and this is absolutely personal preference, it is absolutely no more correct than anything anybody else does. I like to evaluate c as soon as it shows up. So as soon as I do the integral, if I have the means to evaluate c, I'll do it. So I'll do that here. So I know that y of 0 equals 2. So let me make the substitutions and make that evaluation. So 1/2 of 2 squared is equal to negative cosine of 0 plus c. So negative 1/2 of 4, or sorry, 1/2 of 4 is 2. Cosine of 0 is 1, so 2 equals negative 1 plus c, which means that c is 3. All right, so now I'll reinsert that. So I get 1/2 y squared equals negative cosine x plus 3. All right, so now we have a particular solution. We were able to figure out what c was equal to. Same drill, we can isolate y. Now we're going to double everything. So this gives us y squared equals negative 2 cosine x plus 6. And then we'll square root. So y equals the square root of 6 minus 2 cosine x. All right, that's all for 17. 21, another initial value question. So one thing you probably saw in the videos is that, you might have gotten this idea that when you have a bunch of terms added together where the variables are mixed together, so like I have x e to the t, it seems like it's not going to be separable. So we got to do some careful algebra here to get to a place where this is separable. So let's do that. So dx dt. So I have 4 terms here. What can be done? There's no common factor that all 4 of these terms have, but something I can start with, I can factor an e to the t out of the first 2 terms, and that gives me e to the t times the quantity x plus 3 plus x plus 3. And now what I notice is that basically if I treat this as a term and this as a term, I can factor out x plus 3 from either of those. And then I get e to the t plus 1. So if I write it that way, I believe it is, it always was separable, but now hopefully it's more clear that it can be separated. So that becomes, if I divide the x plus 3 over, dx over x plus 3 equals e to the t plus 1 times dt. So separation has been completed, which means we can integrate both sides. So dx over x plus 3, what is that integral? Again, we have a fraction. What is the derivative of x plus 3? It's 1. So this one is a true natural log. So natural log of the absolute value of x plus 3 is equal to, what's the integral of e to the t? It's e to the t. Integral of 1 is t plus c. This time I'll go a little different. I'll carry the c with me much longer just to show that it truly does not matter. As long as you're careful, it really does not matter. So let's isolate x first. So what do I do first to isolate x? Let's exponentiate. So raise e to both sides. And just a reminder, you can't raise e to individual terms. You raise e to the left-hand side and raise e to the right-hand side. So what's e to the natural log of x plus 3? That is x plus 3. And what's e to the t plus c? As much as you would like it to happen, that is e to the e plus e to the e to the t. Or no, it does simplify. I'm sorry, I was thinking of something else. For now, I'll just write it like this. And then we can talk about how that simplifies. So all these exponents are added together. So a refresher I'll give you is this. So if I have x to the 4th times x to the 6th, that's equal to x to the 10th, right? And why is that? That's because you add the exponents together. So I would venture to say that many of you are comfortable going in this direction. Maybe not as much as coming back, but that's essentially what we're going to do here. So now I get x plus 3 is equal to e to the t times e to the t times e to the c. And we're going to kind of take that liberty again. E is a constant, c is a constant. A constant raised to a constant is a constant. If c is already unknown, then I will just kind of absorb those together. X plus 3 equals c, e to the t, e to the t. And we're almost there. Let me give myself a little more room. So now what I have is x equals c e to the t, e to the t, minus 3. All right, so now the last thing we have to do is to evaluate c. So what information do I have to do that? I know that this goes with the origin, essentially. So 0 equals c times e to the 0 times e to the 0 minus 3, which is equal to e to the 0 is 1. So e to the 1 times 1. So ce minus 3. So ce equals 3. C equals 3 over E. So finally, X equals 3 over E times E to the T, E to the T minus 3. For this particular one, I feel like there's probably a lot of different ways to write this equation. And many of you probably wrote it in a way that's less ugly than mine. But this is correct. All right, moving on to 24. All right. Mr. Ratchet, an elderly American, was found murdered in his train compartment on the Orient Express at 7 a.m. When his body was discovered, the famous detective Hercule Poirot noted that Ratchet had a body temperature of 28 degrees. The body had cooled to a temperature of 27 degrees 1 hour later. If the normal temperature of a human being is 37 degrees and the air temperature on the train is 22 degrees, estimate the time of Ratchet's death using Newton's law of cooling. All right, so what does Newton's law of cooling say? It says that the rate of change of temperature with respect to time is proportional to the difference between the temperature of the object, so the variable temperature of the thing that's either cooling up or heating down, or sorry, cooling down or heating up. So the difference between that temperature and the temperature of the room, or the ambient temperature, which needs to be constant for us to think about Newton's law of cooling. So, is this equation separable? Yes, it is. So, actually, before we separate it, let's actually do what is the ambient temperature? The air temperature in the train is 22 degrees. So, we're going to assume that that temperature is going to remain constant. It's a safe assumption. So, we have dt, d capital T over d lowercase t equals k times t minus 22. So how do we separate this? We can separate this in 2 steps. Since this is our 4th one of these, I'll go ahead and handle it all at once. We'll divide both sides by capital T minus 22, and we'll multiply both sides by d lowercase t. So that gives me dt over t minus 22 equals k dt. So Newton's law of cooling says that there's a proportionality here. We don't really have any idea how strong this proportionality is. So we have enough information to find that out, but we don't have it yet. Okay. So where do we go from here? So we have separated variables, which means we can integrate both sides. The left-hand side, we have another natural log. We have natural log of really technically absolute value of t minus 22, but I'm not really going to be dealing with temperatures that are less than 22. So I'm going to just look at the positive side. Natural log of t minus 22 equals k t plus c. Do I want to evaluate c right now? I don't even think. Let's go ahead and catalog what information we're given. When his body was discovered, the famous, so he was found murdered in his train compartment at 7 a.m. When his body was discovered, the famous detective Hercule Poirot noted that Ratchet had a body temperature of 28 degrees. So we'll say this. We'll say that T0 equals 28. So we're going to estimate the time of death here. So this is one of those rare situations where even though we're going to solve for a time, we're going to get a negative number. We're going to go backwards in time, even though you're probably used to never ever dealing with negative values for time. But I think it just makes it easier to say time zero is the first temperature we know about. What else do we know? We know that 1 hour later, actually, is this what I want to do? Oh yeah, I think so. Okay. So time one is 27 degrees. And what do we want to find out? So we're going to solve for a time. So the time of so the temperature at some time is equal to what? So when he was alive, his temperature would have been what? His temperature would have been 37 degrees. So that's the game. We know this information. We know this information. We want this. So let's go ahead and keep solving. I think we can use our first information here to figure out our value of C is. That's partly why I'm saying time equals 0, is so I can get rid of this K. So let's go ahead and plug that in. So the natural log of capital T, 28 minus 22 equals K times 0 plus C. So that basically gives me C is equal to the natural log of 6. So that's valuable. That helps me specify my equation a little more. Natural log of T minus 22 equals KT plus natural log of 6. I have another constant. I think I can go ahead and figure it out now. So I'll go ahead and do that now. I also know that the natural log of 27 minus 22, so the natural log of 5 is equal to KT, so K times 1, K plus natural log of 6, which means that K is equal to natural log of 5 minus natural log of 6, which, if you remember your properties of logarithms, is equal to the natural log of 5 over 6. So now I have both my constants settled. So what's my equation look like now? The natural log of T minus 22 equals T natural log of 5 over 6 plus the natural log of 6. All right, so the game really hasn't changed. I'm trying to figure out when this person's temperature, when Mr. Ratchet's temperature was 37 degrees. So I know a value of capital T. I want to figure out the value of T that goes with it. To get there, I think I need to keep doing some algebra. So let's do some manipulations on the right-hand side here. Natural log of T minus 22 is equal to the natural log of 5/6 to the power of T. Again, this is another property of logarithms we could take advantage of, plus the natural log of 6. One more property of logarithms I can do is if I have the natural log of two things added together, then I can rewrite them like this as the natural log of 6 times 5/6 to the t, and that's equal to the natural log of t minus 22. Okay, why did I go through the trouble there? Here's why. If the natural log of this equals the natural log of this, then I can say that this equals this. And we're one step away from solving for t. So t equals 6 times 5/6 to the t plus 22. All right, so went that far with algebra. I'm going to go ahead and go back to Desmos. And graph this. So f of x equals 22 plus, already forgot it, 6 times 5/6. 6 times 5/6 to the x. And I'm not anywhere near that scale. So here it is. And what do I want to find out? So remember, we're going to look backwards in time. One thing I want to make sure about, what's f of 0? 28. What's f of 1? Okay. So just kind of double checking the fact that the data I want, I mean, that's not absolutely, doesn't prove everything that I did everything right, but it's a good checker. What did I want to find out for sure? I wanted to find out time of death. So I'm going to graph another line here, y equals 37, because that is the temperature of a normal human body. And where do those lines intersect? They intersect at negative 5.02. So let's take that information. So what we have found is t equals negative 5.02. So when do we think Mr. Ratchet was killed? Well, if his body was found at 7 a.m. and his temperature indicates that he was killed 5 hours prior, then we can say that his time of death was about 2 a.m. All right, and that's all for section 1.2.